Welcome back. I'd like to acknowledge that sometimes the sound cuts in and out on these recordings, and I'm sure that's very annoying. If I knew how to fix it, I would, but I don't know what's causing that. So if you have any technical advice for me, please share it. Can we begin with the observation that these speed limit signs have no attached units? It's really ambiguous. I think it's a little presumptuous of the government to just assume that we're all on the same page with our choice of units. I mean, how do we know this doesn't mean 60 miles per second or 60 light years per century? But it is in fact, 60 miles per second. I meant to change that. Let me do that real quick. So suppose you took a trip in a vehicle where maybe you're using cruise control. So you're going 60 miles an hour the entire time, and your trip lasts for 3 hours. Here's a very easy question. How far did you travel if you went at 60 miles per hour for 3 hours? I'm sure most of you, unless you're rusty on your times table, otherwise most of you immediately recognize that you drove 180 miles. So what are you doing in your head to arrive at that answer? Obviously, you're multiplying those two numbers. Let's look at how the units work out. If you multiply this rate, the rate at which your position changes in time, multiply that rate by a time interval, you can see that the dimensions of time cancel and we come out with dimensions of distance. So let's codify this very simple operation that you're performing in your head. You just take your speed, otherwise known as the rate of change of position with time, multiply by a time interval, and that will get you what we normally think of as a distance, but let's be more precise and call it a displacement. So you're familiar with this. You've known this formula for a long time. You probably saw problems in high school math where you had to use distance equals rate times time. But let's try to interpret that graphically. So here's a graph, a plot of velocity versus time. The vertical axis is velocity. And since you're driving at a constant speed, your velocity graphically is just that horizontal line. And this graph here is not going to be to scale. And notice it's okay to just put the number 60 here if you've specified your units up top. It's understood that any numbers on this side are speeds in miles per hour. Same thing over here. I've already specified that the time is expressed in hours, so I could just put the number 3. So we drove from t equals 0 hours to t equals 3 hours, going 60 miles an hour the entire time. And you just, I hope, concluded that the distance you covered was 180. Well, 60 times 3, isn't that the height of this rectangle times the base? And that would give us the area. So perhaps it's just a coincidence in this instance that the displacement equals the area under the v versus t curve, or perhaps it's not a coincidence. Maybe that's going to end up being a general result. But you should take note of that now, that the area under the velocity curve for the duration of the trip has the same value as the distance covered, or I should really say the displacement. Okay, let's ask a slightly more complicated question. What if it's still a 3-hour trip? You start at 60 miles an hour, but now you're going to be gradually pushing harder and harder on the accelerator so that you're steadily picking up speed. And at the very end of your 3-hour trip, you've just reached a speed of 80 miles an hour. Now, how far did you go? Can you do that one in your head? When I do this in person every semester, maybe there's one or two people who come up with a decent answer. And I'll walk you through it if it hasn't occurred to you. If you were just going 60 miles an hour the whole time, you would have gone 180 miles. If you were driving at 80 miles per hour the whole time, 80 times 3 would be 240. So we know it's somewhere in the middle, right? It's more than 180 miles that you traveled. It's less than 240. Well, what number exactly? Let's look at it graphically. Let's look at another plot of velocity versus time. And I specified in a previous slide that your speed increases steadily. See how we're climbing at the same rate? All the way to 80 miles an hour for the entire 3-hour trip. You know, that'd be tough to do in practice. How do you actually take an entire 3 hours to increase your speed only 20 miles per hour, but I'm just trying to keep the numbers simple here. Well, if it's true that displacement is the area under the V versus T curve, then maybe we could figure out what that distance was just by using geometry. And here's one way to do it. Rather than, let me back up here, we could do the area of the rectangle and then the area of the triangle, and we will in fact come back and revisit that approach. Let's instead find an equivalent rectangle. So I've drawn here this shaded rectangle. You'll notice that it's got this extra bit of area here, this triangular wedge that's equal to the extra area that the original shape had. So this rectangle that I've superimposed on the green patch has the same area as the green patch. And we could easily determine the area of this new rectangle because we just use base times height. And you'll notice that the only way to get the area of the triangles to be equal is if the height here is 70. So 70 miles per hour times 3 hours would be 210. Seems like a reasonable answer, right? It's more than 180. It's less than 240. In fact, it's right in the middle. So if we want to use this equation still, displacement equals velocity times time, it obviously doesn't work if we plug in the initial speed of 60. 60 miles per hour times 3 hours is 180, but we just concluded that we go 210. So is there still a way of using this equation and replacing 60 with some other speed? Well, the overbar notation again means average. So this formula still works if you use the average speed. And evidently for this example, that average speed was 70. In fact, this really shouldn't be surprising that we can still use this equation, because if you solve it for V bar, which is V average, you get the definition of V average. So that's really all this is. We've already defined average velocity as the total displacement, in this case, 210 miles divided by the total time of 3 hours. 210 over 3 would give us the 70 miles per hour. So take the definition of average velocity and solve it for displacement, and you get this equation. You can always use this equation provided you know what that average velocity is. In this case, it's 70. So I want to emphasize now that this equation is always true. Later in this presentation, we're going to focus on situations where the acceleration is constant, but this equation works for any type of acceleration as long as you know what the proper average velocity is. So consider a related example. What if this time it's still a 3 hour trip, you still start at 60, but you stay at a speed of 60 miles an hour for almost the entire trip? Like I said, this is not to scale, obviously, but what if you went 60 miles an hour for the first hour, the second hour, and then just like the last minute of your trip, you step on the gas pedal and scoot on up to 80 miles per hour just as you're finishing that 3 hour trip? All right, now, how far did you go? Did you still go 210 miles? Would that be reasonable? Most of you are probably thinking, no way. Because if we try to find that rectangle that has the same area, I tried to estimate the height of a rectangle whose area would be the same as the area under this original curve. See how the original curve doesn't have this area, but it does have this extra bit here. And I tried to make them roughly equal. So if the height of the equivalent rectangle is the average velocity, remember in the previous example, the height was 70, that's the rectangle with the same area. If that's the case, then the average velocity here, which is the height of this rectangle, is clearly not 70. It's much lower. And that makes sense. If you spend almost the entire trip at 60 miles per hour, then your average speed should be really close to 60. It should be much, much closer to 60 than it is to 80, because you only jumped up to 80 at the very end. So this is not something you need to know for this chapter, but a lot of you will have no problem understanding this anyway. What you would actually use to get the average velocity is the mean value theorem for integrals, which you probably encountered in your first semester of calculus. Just think about the rectangle. Since the area of the rectangle is base times height, if you take the area of the rectangle and divide by the base, that will get you back to the height. See how that works? Take the area, divide by the base to get the height, and the height is the average velocity. So the area under the velocity curve between 0 hours and 3 hours, that's what we call the integral from 0 to 3 of v dt, and then divide by the width of the base to get the height. In a calculus class, they would probably write it something like this. Usually the function that we're talking about is labeled f of x. That's exactly what this is. So for future reference, in the most general case, you would compute average velocity by taking the area under the velocity curve, which we're going to see is displacement, and divide by the time interval. Now, if the velocity is increasing at a steady rate, like the first example I brought to your attention, then it seems pretty clear that the average is just halfway between the 60 and 80, halfway between the initial and final velocities. The number smack dab in the middle, you probably know that's called the, well, that's literally the average. That's the arithmetic mean. How do you take the arithmetic mean of two numbers? Add them up, divide by 2. Okay? So this formula for average velocity will work provided that your velocity is increasing at a steady rate. Here it's obviously not increasing at a steady rate. It starts out not increasing at all, and then it rapidly increases. In fact, you can see that the slope itself is increasing. So that formula is not going to work here. If you take 60 plus 80 divided by 2, you get 70. 70 is obviously not the average velocity for this particular motion. Okay, so we can codify that with an equation. Provided the velocity increases at a steady rate, you can go ahead and just add the initial and final velocities, divide by 2, and call that the average velocity. So I'm realizing here that I'm really using the word average in two slightly different ways. There's the arithmetic mean, where you literally add two numbers and divide by 2. And then there's this more general notion of average, for which you'd have to use this formula. And this formula will give you the same answer, 70, if your velocity is increasing at a steady rate. And I put a box around this because I'm going to keep a collection here as we go forward, keep a collection of all these equations that are commonly called the kinematic equations, because you will be using these over and over, ad infinitum, ad nauseum, ad pucum throughout the semester. So can we put that in more precise terms, a velocity that steadily increases? We've got some vocabulary now. The rate of increase of velocity, rate of increase, that's change in velocity per change in time. That's just the slope, right? And that's what we call acceleration. So a steady increase in velocity would mean a steady or constant rate of change. In other words, a constant acceleration, constant slope, simple as that. So if you're looking at a graph, not of position versus time, but velocity versus time, and you see that the velocity is increasing at a constant rate, that's the same as saying constant acceleration. Because what is the rate of increase of velocity? By definition, that's acceleration. So rather than saying that you can use this formula for steady increases in velocity, it would be more precise to say you can use this formula for average velocity if the acceleration is constant. Simple as that. Okay, so got my blue box around it, and I'm reminding you only applicable for constant acceleration. So we have two formulas so far that commonly fall under this category called kinematic equations. You will have occasion to use both of these. Never forget this one. It's really just the definition of average velocity. So you shouldn't have any trouble remembering that one. This is also simple, but you have to remember when it's applicable. Now, let's go further. Can we relate the final velocity to other information that we may have, including the initial velocity? So I'll remind you from the previous presentation and something you should have read about in your book. Here on Earth, on the surface of the Earth, if you throw something up into the air that's dense, so it doesn't, so it's not affected too much by air drag. So we're not talking about a piece of tissue paper or a Kleenex. If you throw a rock up in the air, it immediately begins to slow down by 10 meters per second every second. More accurately, it's 9.8. On the way down, it's speeding up by 10 meters per second every second. We talked about that. That's the free fall acceleration, or g. It's the value of g here on this planet, near the surface of the planet. Let's make it more interesting, because I don't want to talk about just throwing rocks up into the air. So how about you throw a cat, or you drop a cat straight down from the edge of a tall building, but let's be humane about it. And we've got a big bean bag at the bottom. So this fluffy cat's not going to be injured. And we don't want to contend with air drag. So let's put this whole thing on the moon to make it more realistic, right? Because we always model, in this class, we're always modeling things as if there's no air drag, but in real life there is air drag. So I will make it more realistic by putting it on the moon. And that means Space Cat needs a helmet and you know, some pressure regulation inside that spacesuit. So we don't have to worry about an atmosphere, but we do have to contend with the fact that the free fall acceleration is lower on the lunar surface. By the way, this is a real photograph, I believe. And if you're wondering why the stars are so bright, that's a long exposure. If you leave the camera shutter open and point it at the night sky, it's going to gather a lot of light. You'll see all those stars. I think this photograph is called Earthrise, if you want to Google that. So on the surface of the moon, the free fall acceleration is much lower. It's something like 1.6 meters per second squared. We've got famous kitty astronaut in the corner here, Fuzz Aldrin. I believe he did most of his missions back in 1969. Let's make this number easier to deal with. So we'll just round it to 2 meters per second per second. That's grossly approximate, but it works. Fuzz's buddy, Mew Armstrong over here. So here's Space Cat. He's been dropped from the edge of a building. He's accelerating towards the lunar surface with a beanbag, and he's speeding up at 2 meters per second per second. Easy enough. Ask yourself this, or I guess I'm asking you this. If Space Cat falls for 3 seconds towards the lunar surface, and he's picking up speed at this rate, how fast is Space Cat moving after those 3 seconds? I hope that's a really easy question for you. If it doesn't seem easy, you're overthinking it, because it really is straightforward. If you're picking up speed at 2 meters per second every second for 3 seconds, you should be going 6 meters per second at the end of that time interval. Simple operation. It's very similar to what you did just a moment ago with the car speeding up. We took a rate. In that case, it was the dimensions of the rate were different. Instead of meters per second, it was miles per hour. So only one time unit was downstairs. But you know, if you're going 60 miles per hour for 3 hours, that's 180 miles. Here we're picking up speed at 2 meters per second time. So we're still multiplying a rate by a time interval and getting something with different dimensions out. And check how the units work out. See how you've got seconds squared downstairs and second upstairs. One of the seconds cancels. The meters are still there, and we get this. So if you can, get in the habit of casually glancing at the units and making sure that everything works out. It's kind of satisfying to see that it does. It makes you feel like you're understanding things a little better. Once again, let's codify that very simple operation. If you take the rate at which you're picking up speed, also known as acceleration, or I should say the rate at which your velocity is changing, and you multiply by a time interval, that would give you your final velocity. That's exactly what we did here. So this is a more general result. You don't need specific numbers. You can plug in any numbers. Let's make this slightly more complicated. This time, instead of just dropping Fuzz towards the lunar surface, you chuck him straight down. He's got a beanbag, don't worry about it. You chuck him down at 5 meters per second, which is over 10 miles an hour. And then you let him fall for another 4 seconds. So let's not worry about the fact that he might actually hit the beanbag before the 4 seconds are up. Let's pretend this is a really tall building in some lunar colony. So think about it. How fast will he be going at the end of those 4 seconds? Put on the Jeopardy music. Let you think about that. Well, if you had just dropped him instead of thrown him, then after 4 seconds, you're picking up speed at 2 meters per second every second times 4. You would be going 8 meters per second. But since you were already going 5, it seems reasonable that you would just add those two numbers, right? This is the additional velocity you gained, or additional speed, due to the gravity field, but you were already going 5 meters per second. That would put you at 13 meters per second. And if that was your answer, you are correct. Let's once again write this algebraically. Let's generalize it so that it's not just specific to these numbers. your final velocity after accelerating in free fall for some amount of time would be whatever your initial velocity was, plus the change in your velocity due to the acceleration. And this formula actually works whether you're launched downwards, upwards, whether your acceleration points down as it does for gravity or up. It's very general. As long as you're using the appropriate signs, SIGN, this will work for any scenario. So it's a very intuitive result, but by making an equation out of it, it allows us to do things that we might not be able to do with mental math. Let's also subtract V initial from both sides and write this in a slightly different form. That would get rid of V initial here. Over here, you'd have V final minus V initial, which we call delta V. So this might be a better way of writing it. The change in your velocity is merely acceleration times time. You should memorize that. Look how similar it is to delta X equals V delta T. Almost the same equation, right? Instead of displacement, delta X, is velocity times delta T. This is actually change in velocity is acceleration times delta T. Now, I don't want to go back a bunch of slides, but remember what has to be true if you plug velocity in here? If you're doing delta X instead of delta V, displacement is velocity times time. You can only use that if you're using the average velocity. I guess I will go back real quick. Sorry. If you have issues with flashing lights, look away. You can only use this if you're plugging in the average velocity. And by the same token, this equation is actually only valid if this is the average velocity. Now, the example we're considering is acceleration from free fall, and that is constant, so we don't have to worry about it. So when you see this equation, it's actually understood. You can only use this equation for constant acceleration. If the acceleration is gravitational, then as long as you're talking about motions near the surface of a planet, you can just pretend that it is constant. Okay, so now I've collected all three of those formulas that we've just taken a look at, because these are all called the kinematic equations. We're not done yet. We've got a couple more to look at, but it really would behoove you to memorize these. And it would be nice if you just ended up memorizing them naturally by doing lots of homework problems. If you've gotten enough practice, you'll have these memorized anyway. And if you really understand their meaning, there's really nothing to memorize. You've got the meaning memorized, not so much the equation. That's my advice to you, is if you can really internalize what these equations say, then you'll already have them memorized. But at the very least, you'll want to have these on a note card when you take your exam. I'm going to talk more about this, but even though you're going to be recorded during your exam, you can still have a small note card next to you with formulas and such. Okay, I pointed out already, there's another way to write this. Delta V, that means final minus initial. We could put the initial velocity on the other side. This is an equally valid way of writing the equation. Sometimes it's a little more useful. And now let's do the following, because where I'm going with this is a few slides back, I gave that silly example about starting out at 60 miles an hour, ending at 80 over a period of 3 hours, and I asked, how far did you drive? And most of you probably didn't come up with the answer right away. It would be nice if we had a formula that would give you your displacement, even in instances where you're accelerating, like that example. So let's take this expression for final velocity and substitute it into this equation, which tells us the overall average velocity. Remember, that only works for constant acceleration, because then we're going to have a formula for V average, and we can plug that in here. And at the end, we'll have a formula that you may not have seen before for total displacement. And it's a formula that you will use many times this semester. You'll even see it in 3B if you take 3B. So here goes. This blue expression goes in here for V final. This is what I get. Now, what's V initial plus V initial? That's 2 times V initial. And now we'll distribute the 2. Division is distributive. So 2 V initial over 2 is just V initial. And then this will give us a 1/2 A delta T. So here's our new expression for the average velocity. And this is not so intuitive, is it? Like with the example of starting out at 60 and driving for 3 hours, picking up speed steadily the whole time, I don't think it jumps out at you at all that what you could do is just say, hey, well, take 60 plus 1/2 times 3 hours times whatever that acceleration is. Let's see, you went from 60 to 80 in 3 hours. That's 20 miles per hour in 3 hours. Well, evidently this formula would also give you the average velocity, which we know to be 70 in that example. Okay, now that we've got this formula, plug that in here and distribute one more time because multiplication is distributive. We've got a v initial times delta t, and then what do we have here? 1/2 a delta t squared. You may have heard the phrase 1/2 at squared before. Your book likes to put emphasis on the fact that it's really a time interval. It's the change in 2 times, and I like that, so I'm going to stick with that notation. And there it is. What we've done is synthesize some previous results, none of which were complicated, right? All that stuff was common sense. My questions about throwing Space Cat off the building, it was easy to answer those questions, but we've put those, after codifying those mental procedures into simple equations, we put them together and arrived at something that's really not so obvious. This one you should also memorize, and you will have it memorized because you're going to use it a lot. And again, this equation is only applicable for constant acceleration. What it says is your total displacement during your travel time has 2 contributions. There's the one you've known about since like 8th grade or before, distance equals velocity times time. But there's this additional contribution because you're speeding up or slowing down. Your velocity is changing. Right? So you just want to memorize. You could just memorize 1/2 at squared, right? And know that you have to tack that on to the very familiar velocity times time. So 1/2 at squared, 1/2 at squared. Just, get up in the morning, say it a few times. Say it a few times before you go to bed. Irritate everybody around you. Or just let me say it a bunch of times, 1/2 at squared. Maybe you've already got it memorized. Now, you'll notice that if you are not accelerating, if you're driving at constant velocity, a would be 0. This term goes away, and you would just recover the regular old delta x. So, or delta x equals velocity times time. So this newer formula includes the old result as a special case. It reduces to distance equals velocity times time in the case of 0 acceleration. All right, so here's all 4 of the equations we've looked at, and I'm separating them into equations that deal mostly with velocities and then equations that have the displacement in them. We're still not done though. We're gonna have, I believe, one more formula to look at. Yeah, you can see I very tellingly left some space here. Maybe you were thinking, hey, that's not very feng shui. There's this hole in the screen. Because we're gonna plop one more formula down there. And yes, they call these the kinematic equations. Kinematic meaning just having to do with motion. And if you think about it, we're not doing any physics yet. All the stuff we're doing is really just math. So we're building a vocabulary before we're ready to tackle the dynamics. Kinematics is just, it's like the vocabulary of motion. We needed to establish what exactly velocity is, average velocity as distinct from instantaneous velocity. We needed to establish what acceleration was. So once you build up that vocabulary and you get some facility with these equations, then you can start talking about what causes the motion. That would be force. What produces the acceleration. That's the content of Newton's laws, which we'll get to shortly. See the emphasis here on constant acceleration? This equation, and this equation. Oops. This one, and this one are only valid for constant acceleration. I would like to say a word about alternative notations because you're going to see them. I'll be using different notations in these presentations. If you pick up another book for some supplementary learning, or if you're taking another class in the future, you'll probably see alternative notations. There's no reason we have to refer to the final velocity as VF or the initial velocity as VI. What else could we do? Oh, yeah, first, don't forget, delta T is a time interval. It's really final time minus initial time. But almost nobody writes it this way because it's a little tedious. But don't forget that the velocities here correspond to these times. This is the velocity that your particle or car or falling space cat has at that time. This is the velocity that it has at that time. You don't want to forget that. But we're going to stick with the delta t notation. Also, instead of final and initial, we could just label the times, t1 and t2. And then the velocity at time t2, we can call v2. And v1 would be the velocity at time t1. But again, there's no reason that the numbers have to be 2 and 1. We could just as well go with 1 and 0. So v0, which is usually pronounced v0, v0 could be the initial time, and v1 could be the final time. And here's the last thing that you'll see quite often. A lot of books like to do this. They think of v0, v initial, as a constant, like it's already been determined. And then your final velocity is your velocity at any time. It's like a variable. T becomes a variable, and so the velocity at that time is also a variable, and they just call it v. That's a little more flexible. So you're going to see all of those notations. It's understood here. This is the velocity at time t0, which is often taken to be 0 seconds. And this is the velocity at some final time, which is often just called t. Okay? I like the way your book does it. It's very clear. There's one more equation that we need to produce here and add to our list of so-called kinematic equations. And this next equation, you may end up using more even than this one. So let's eliminate one of the quantities here, because we've got a number of, we've got initial and final velocity, acceleration, time interval, and displacement. What is that? 5 different quantities, arguably. A lot of times the problem you're doing does not require that you deal with all of those quantities. And in fact, very often, the time interval is not spoken of or needed. So it would be nice if we could relate some of these quantities without having to mess with the time. So what we can do is eliminate the time from these two equations. This is an algebraic technique where if you've got a set of equations, you can eliminate one of the unknowns from those equations. So let's start by solving this one for delta t, which I've done here. You should check that in your head. And so we've got this expression for delta t that we can now plug into here and here. So we're substituting, really. Once you do that, and should I take the time to do that here? Should I work out all that algebra? Or we'll just apply some magic here, and this is what you'll arrive at. If you're a little compulsive about following all the steps, that's a good thing. You can check that this is what happens. But you should arrive at this formula. And I put another blue box around this one because we're going to add it to the list. Get cozy with this equation. This equation is your friend, not your enemy, because you're going to use this equation an awful lot. And its content is very intuitive. It actually tells you some stuff that you kind of already know. It's just expressing it precisely. Yeah, I just discovered these transitions recently. I want to see that again. That was so cool. Okay, I think we're ready for the complete list of kinematic equations after that long-winded development. You should definitely memorize these, or just pull up this presentation and watch that transition every time you need the equation, or tattoo them to the back of your eyelid. That seems kind of permanent though. So you could argue that there are 5. This one's really just the definition of average velocity, right? That's been solved for displacement. So do not forget, these are the kinematic equations for constant acceleration. Now, because you guys have taken calculus, you've been let in on the secrets of the calculus. You have this great wisdom. You're actually capable of finding analogous equations for many types of acceleration. And we are going to look at that. Non-constant acceleration. Like if you know how the acceleration depends on time, we're going to see that all you have to do is integrate twice to get the position at any time. It's really not that hard. We will take a look at that. But most of the time, these kinematic problems will deal with situations of constant acceleration. So these are the ones that you want to be most familiar with. And now we should probably use these equations to solve a couple problems. I like to start with this one. There's a building over in Dubai called the Burj Khalifa. I'm probably butchering that. Burj, I don't know how to pronounce it, but it's really tall. I mean, it's really tall. This is, well, that's less than a kilometer. Let's just say this is like half a mile high, if you can believe that. Suppose you went to the very tippy top, I would never do that, and you dropped a bowling ball after making sure that nobody was down here, of course. It's like a holiday, nobody's there. Drop a bowling ball. Let's not worry about air drag. Pretend there's no air drag. How long do you think it would take for that thing to hit the ground? Think about it. It's kind of fun to ponder, because if you haven't had much practice with this sort of thing, your estimate might be really lousy. You know, maybe some of you are thinking, I don't know, 30 seconds, which you're going to find out is ridiculous. But we can easily answer this question with our kinematic equations. But first, let's watch a video of some crazy people jumping off that building. Some people have an unfortunate genetic condition where they're not afraid of heights. I pity those people because it's a very good survival instinct to be afraid of heights. But here's two of those unfortunate souls, and let's watch them for our entertainment. I'm sorry about that. Let me pause. Yeah, up here in the desert where I'm living at the moment, you just can't get good internet service, but that's the price you pay for being away from all those people. Okay, you get the picture. They're making it seem like it does take 30 seconds to get to the bottom. But what we're watching here is not really the same as the bowling ball, because they're going to experience significant drag on their clothing and their bodies, especially once, you know, the wingsuit goes out. That's the whole point, right? Towards the end, you need to have drag so you can slow down. But you can see it's a very tall building. So now for the first time, let's use an equation to solve a problem. We're getting into quantitative stuff here. The very first thing you should probably do when solving any of these problems in chapters 2 through 4 and onwards, because you're going to continue these techniques throughout the semester, first thing you should do probably is choose your coordinate system. And the most natural choice is to have two axes. They need to be perpendicular, but usually you're going to have one axis vertical and the other horizontal. Sometimes we'll go with tilted axes when it makes things easier for us. And I've chosen to say that up is the positive y direction, which is not the only choice, but oftentimes it's the most intuitive one. And you'll notice that the origin is down here, and that might be a little awkward because if we're dropping the ball here, then why do we want to deal with x coordinates over here? And that's because I've made that choice because all we care about is the vertical motion anyway. And in that respect, my origin is a sensible choice because I put y equals 0, the ground level, at the actual bottom of the building. Okay, you could put the origin way up here, which is at now the top of the building. This would equally make good sense. And I could have done it this way with the y-axis still being positive up, but now I've chosen to make it so that the positive y-axis points downwards. That's perfectly valid as well. And the difference between those two, I don't want to dwell too much on this point right now, but we know that the gravitational acceleration points downwards. So if you call up positive, then the free fall acceleration would actually be negative g, or negative 9.8. Remember, g is just the absolute value. G always means positive 9.8. So if you want to call up positive, then the acceleration of free fall is really negative 9.8. In this case, if you call down positive, then the acceleration, which also points down, would actually get a plus sign. And maybe that confuses you at first, but trust me, well, don't trust me, trust the book, just try it yourself. You'll see that the physical results come out the same either way. it doesn't matter how you set up your coordinate system. That's not going to affect the physically meaningful result at the end of your calculation. Okay, I looked up the height of this building. Oh yeah, you've seen this number, 828 meters. And it's also very useful in many problems to do this, to explicitly write down or decide what your relevant times are and give them labels. It's not always necessary. The more practice you have with these, the less you're going to need to be real clear like this. But I'll say right now that when it comes to exam time and partial credit, you do want to show as much of your thought process as possible so that I can award the maximum number of points. T0, I will choose to use the label T0 for the moment at which this bowling ball is released. And then T1 is the time at which it hits the ground. So T1 does not mean 1 second, far from it. It's whatever time, it's the time at which the ball hits the ground. Could be 10 seconds, 20, we're gonna find out. And it's also sometimes useful to make explicit which quantities you know going into the problem and which quantities you're looking for, because that will help you decide which of these kinematic equations you should use. So we actually do know what the vertical displacement is. The ball is going to start here, and it's going to move through a distance of 828 meters. Now, displacement isn't just distance. It also involves a plus or minus sign. In this case, because I've called up the positive direction, the ball actually suffers a negative displacement. Yes, it moves through a distance of 828 meters, but its displacement precisely is negative 828. That'll really help you set up problems if you remember that displacement has a sign associated with it. We do know the acceleration because by assumption, it's in free fall and we're not worried about air drag. Now, in reality, a bowling ball will experience drag, and so it's not going to pick up speed quite at 9.8 meters per second. It's going to have a reduced magnitude of acceleration. How much the difference is, I couldn't say off the top of my head. This one's kind of subtle. Very often, some of the information you have is implied. It's not stated outright in the problem. You'll notice they don't say, the way I phrase the problem, I don't give you the speed at which it was dropped. Because if you're just told it's dropped or it's dropped from rest, the assumption is that your initial velocity is 0. And you should think about that for a moment. When you drop something, it looks like it's immediately moving, right? And that's because it doesn't take long at all to be moving or to pick up speed to a speed that's noticeable. But if you were to record yourself dropping a hammer at like 500 frames per second and watch it in slow motion, that hammer, when you first release it, it does appear to be almost motionless. So if that's not obvious to you, make sure you understand when you drop something, quote, from rest, it's not moving at that first instant. Now, how long does it spend not moving? Again, it spends no time, no finite amount of time. It immediately picks up speed. It immediately begins accelerating at 9.8 meters per second. Okay, and what we're looking for is the time interval. How long does it take? What's the duration between T0 and T1? I don't remember adding that transition. Oops. Okay, let's go back to our list, and this is something you will be doing habitually. When you first start out, you probably want to have a note card with all those formulas written on them. Eventually, you'll have enough practice that you'll just kind of be able to do it in your head, I hope. Just figure out which formula to use. Here's the way I would think about it. Look at what you're given and what you are interested in and figure out if any of these equations will allow you to solve for that unknown in one shot. Because remember, if you're going to deal with only one equation, there can only be one unknown in that equation. If you're dealing with an equation that has 2 unknown quantities in it, you're going to get stuck. You can't solve one equation for 2 unknowns. So is there a single equation that contains all 4 of these? Well, before I answer that, these transitions, let me turn these off. Okay, well, something I'm noticing is that this equation down here contains 3 of the quantities that we're dealing with. Let me get the laser pointer back. Now, when I wrote these equations originally, I was imagining motion along the x-axis, but they work for any axis. There's nothing special about horizontal motion. you could equally well apply these equations along any straight axis. So delta x in this problem would correspond to delta y, the vertical displacement. We've got an acceleration here. We do know that in this problem. And in this notation, I'm calling it the initial. The way I set up the problem just now with the Burj Khalifa, I call the initial velocity v naught. So perhaps we're on the right track here because 3 of the quantities we're dealing with show up in this one equation. However, the one that we're interested in, delta t, does not appear in this equation. Do you see though that because we know this, and this, there's only one unknown in this equation, and that's v final. So we could use this equation to find the final velocity of that bowling ball right before it strikes the ground. All we have to do is plug in the initial velocity of 0, the free fall acceleration, and the 828 meters and take the square root. And then once we know the final velocity, we could go up to this equation. Because delta v means final minus initial, now we would know both of those quantities. Again, we know the free fall acceleration, and then we can solve for delta t. So one way to solve this problem is a 2-step procedure where you use these 2 equations to get to the answer. You kind of leapfrog to the final. And that would work just fine. Sometimes you may recognize that there's a quicker way to do it. So for this particular problem, this equation will allow us to solve it in one shot. Because look at the quantities in this equation. We know this one, that's the vertical displacement, 828. The initial velocity is 0. We know the free fall acceleration. So there's really only one unknown in this equation, and that's delta t. And we can use it to solve for delta t. So that's how I will solve this problem. And I'll be very clear with the setup here. Remember, y0, y naught, is the position of the ball at time t naught. That's the advantage of the use of subscripts. This is the coordinate of the ball at that time. And because I put my origin down here, this is y equals 0. The point at the top of the building would have a y coordinate of positive 828. Now, y1 is the coordinate corresponding to time t1, and I've chosen that as the time when the ball strikes the ground. So what is the y coordinate when the ball hits the ground? Because of my choice of coordinate system, the coordinate down there is going to be 0 meters. It's on the ground. And again, you want to be really careful when you substitute for the acceleration. Why am I going with negative g? G is an absolute value, but because up is positive in my coordinate system, the acceleration needs to be negative 9.8 meters per second. And here's that where we infer that the initial velocity is 0 because we're told that the ball was dropped from rest. Okay, so I've rewritten that kinematic equation, I'll call it the 1/2 AT squared equation because of that second term. And I've rewritten it with a vertical displacement instead of delta x. So I'm just adapting it slightly for this problem. And now I recognize that this term can go away because we're going to plug in a value of 0 for v naught. And now we're just left with this. Delta y equals 1/2 a delta t squared. We're interested in delta t. Now, many of you, if you were working this problem on your own, hopefully you're doing that right now, you may choose at this point to go ahead and plug in negative 828, negative 9.8, move stuff around. But I would encourage you to, as much as possible this semester, wait until the end to plug numbers in. I would solve algebraically first for delta t. One reason for doing that is you're creating like a log of your thought process and your steps. So if you happen to plug in, let's say you've got real fat fingers and you're mashing the wrong buttons on the calculator, you get the wrong number at the end. Well, if I see all your work and everything was correct up until that last step, I might not take any points off out of a 20-point problem. Or maybe I'll just take like 1/10 of a point off just to spite you, but that's inconsequential. Whereas if you didn't do the algebra on paper, so you didn't show much work and you still wrote down the wrong number, I can't give any credit for that. And if this is a homework problem you're talking about, when you go back and look at your work to see what went wrong, there's not going to be any record of it. So try to do things symbolically, plug in numbers at the end. Sometimes it's not really worth the effort because the the formula gets so unwieldy. And we'll see examples of that later in the semester. Okay, now you have to be careful again. Don't just go plugging in the number 828. You know, we know that it falls through a distance of 828, but what if you had plugged in 828 and then negative 9.8 downstairs? You would have to take the square root of a negative number, and then you would have a conniption fit because you probably haven't studied complex numbers much at this point, and your head would explode. That's not supposed to happen. We're not dealing with, quote, imaginary numbers in this class, although they end up being very useful in physics. It's really fun as you go deeper into the subject to see how useful these so-called complex numbers are. And it's an unfortunate name, complex, because it sounds kind of snooty, like it's really complicated. It's not at all. I think the word complex is a translation from German. So it's just some unfortunate original choice in the name. Okay, so delta, that really means final minus initial. My final y coordinate is 0 on the ground, and my initial is positive 828. Or you could just recognize, again, the displacement is in the negative direction. So you could just evaluate that directly. It's displaced by negative 828 because it goes down. See how the two minus signs cancel now? And I find it takes a whopping 4 seconds. That's with no air drag too. If you were jumping off that building like an idiot in a base suit, and I'm just jealous that those people have the guts to do that because I wouldn't, but it's going to take even longer than 4 seconds in real life because of the air drag. In actuality, your average acceleration would be lower than 9.8. So if you're plugging in a lower number in the denominator, that would tend to make delta t come out bigger. Okay, now where am I going with this? Right, let's look at this equation more generally, rather than plug in the specific numbers from this problem. Because very often you will be doing problems where there's something dropped from rest and it falls through a height h, or the opposite. It could be that you launched the ball upwards through a height h and comes to a stop briefly before turning around. And by briefly, I mean, no time at all. That's like the reverse situation. So for those problems, we could refer to the displacement. Let's go with the original case of something falling down. So the displacement would be negative height, because it's in the negative direction. The acceleration, pardon me, is negative g. You see that the minus signs cancel, and we get this result. If you're good at memorizing things, I would just commit that one to memory as well, because it's very useful. What's the difference between this result and this result? There's the added stipulation that the initial velocity is 0. So, you could have thrown the baseball or the bowling ball downwards at some initial speed and still used this equation. You would just have to plug in what that initial velocity was. But this is applicable to the more restricted set of problems where the object is dropped from rest. 1/2 gt squared. I'm saying gt squared, where t is really short for don't get delta t as a time interval between dropping and hitting the surface or whatever. You could also solve this for delta t. I kind of have this memorized now because I've just seen it so many times. You guys are taking this, most of you, for the first time, so you don't need to memorize that. You don't need to memorize either of these results because they both come from what? They both come from this kinematic equation. This is the more important, more versatile result. So if you've got limited RAM in your head for memorizing stuff, stick to this one. Of course, if you don't want to memorize anything, you don't even need to memorize this. You're going to see all you need to do is know how to do calculus, because you can just start with your acceleration, integrate twice, and you've got your position. So all of this stuff's unnecessary. That's really the remarkable thing about this class, and I'll be reminding you of this as we go on. One thing that makes this class different from a lot of others that you may have taken is just how few results are needed. It's more about understanding concepts and knowing how to synthesize them. I know that's a cliched word, but it's amazing that with, I would say, really a list of like 5 items or less, you can develop the entire curriculum of this class, which is something I didn't realize until I had been doing it for several years. Because, when you look at the syllabus, there's 12, 13 chapters that span hundreds of pages. Believe it or not, you could just write a few bullet points on the palm of your hand. And if you understood math if you understood how to use calculus well enough, you could develop the entire curriculum from that. And I don't think that's true necessarily of other subjects, certainly not biology. So in that sense, those subjects are more difficult. Let's look at another example now. Here's a planet named Leo. Oh, no, I'm sorry. That means low Earth orbit. That's an acronym for low Earth orbit. It describes the size of the orbit of this looks like a communication satellite whizzing around planet Earth. And then way out here, I think this is geosynchronous orbit, which would be like something sending satellite TV data down. We will talk much more about this in chapter 13 towards the end of the semester. But I happen to know from having done this class so many times, there's one particular speed at which a satellite must move if it's orbiting the Earth near the surface in a circle. And this is approximately that speed to 1 sig fig. It's 8 kilometers per second. That's about 5 miles per second. So 5 miles, what is that, like the distance between Long Beach maybe and Paramount? Imagine traveling over all those city blocks in 1 second. That's how fast those satellites are going that orbit close to the Earth, including the International Space Station. Now recently, SpaceX, which is based out of Hawthorne, they launched the Falcon 9 rocket, multi-stage rocket. Is this multi-stage? I think it is. And at the top here is payload, which happens to have people in it this time. And I think this is called the Crew Dragon module. And they launched that in May. A lot of you probably watched that. Yeah, that's what I'd be saying. Especially if it was on its way to Mars. Count me out. I will stay right here on Baby Blue. Let's watch a video of that launch.
Stage 1 tanks pressing for flight.
T-minus 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. Liftoff of the Falcon 9 and Crew Dragon. Go NASA, go SpaceX, Godspeed, Bob and Doug.
America has launched. It so rises a new era of American spaceflight, and with it the ambitions of a new generation continuing the dream. 20 seconds into flight, stage 1 propulsion is nominal.
Unreal. Well, there's loads more of that on YouTube if you want to watch more of that. I'm showing this to you because I just pointed out in one of those slides. Let me go back to that. I had just pointed out the speed at which you need to be moving to be in orbit around planet Earth. And that rocket, in fact, that particular launch was carrying astronauts to the space station for the first time. That's what made it historic. It was the first time, I believe, a private company had taken astronauts up to the space station, rather than NASA coordinating it. So if you have to get those astronauts up to 8 kilometers per second, I mean, that's really fast. And they were not moving that quickly in that video. That rocket had just lifted off. It was just gaining speed. So a rocket is a way of getting people or astronauts or supplies up to that speed very gradually. I say gradually, but I think it happens in like half an hour or less. That's one way to do it, is to put people in a giant, capsule that shoots out fire from the back end, and over a period of 20, 30 minutes, something like that, get them up to this very extraordinary speed. But the problem with doing it that way is it's extremely inefficient. Here's the space shuttle, which was discontinued when you guys were kids probably. Look at this enormous fuel tank. You've got the solid rocket boosters. I was just reading about those. I guess they're cheaper, easier to work with. But then you've got all this liquid tank in here, and insanely heavy. I mean, this thing's really large if you can't tell. Google it. I forget how many thousands or tens of thousands or even hundreds of thousands of pounds of fuel is in these ginormous tanks. And what is most of that fuel being used for? Think about it. And the whole point is to lift the rocket, presumably to lift the people inside the space shuttle, get them up to the space station, or just to be in orbit and do some cool science up there. So you might be thinking that the purpose of the fuel is to lift the astronauts or the payload, but most of the fuel ends up getting burned just to lift the rest of the fuel, right? You can't lift this fuel for free. So you're burning fuel to lift the other fuel. And I think it's over 90% of the fuel, I should say the energy, over 90% of the chemical energy liberated is just used to increase the gravitational potential energy of the fuel. Don't quote me on the 90%, but it's way up there. So it would be nice if there were another way to get people up to that speed that wasn't so inefficient and expensive. So one notion that's been floated is the space catapult. This is an artist rendering. You could use a rail gun. Those are pretty cool to read about. After you've taken 3B, if you have learned the laws of electricity, magnetism, you will totally understand the principle behind a rail gun. There's so many things you can understand after you've taken 3B. So don't be intimidated. Yes, you've heard it's a challenging class, people struggle, but it's a very cool class. The idea is to have a very long track and use magnetic repulsion, I'll say, keep it simple here, to accelerate your spacecraft up to that low Earth orbital speed without the use of rocket fuel. And basically it's like right out the gate. You're supposed to get up to that extraordinary speed over a much shorter distance than what a rocket does, which is to rise all the way through the atmosphere. It's still a rather long track, but nowhere near the distance that a rocket travels up through the atmosphere. So these are all just fanciful pictures I found on the web about space catapults. Is it ever actually going to happen? Let's take a look here. Here's a typical runway. I looked up the value. 1,800 meters is almost 2 kilometers, so that's a little over a mile. Okay, I believe I did that right. Yeah. And let's ask ourselves, if you actually launched astronauts off a runway at low Earth orbital speed, you got them going from 0 to 8 kilometers per second from one end of a runway to the other, what kind of acceleration would they be subjected to? Because that's an important question. Let's find out if it's comfortable, much less survivable, or if it's survivable, much less comfortable. I forget which way I should say that. So we'll be very procedural about this and make it easy to implement our kinematic equations. We start from rest in this catapult. When we leave the runway, we need to be going at 8 kilometers per second. So obviously, or evidently, I'm labeling my two relevant times here, T0 and T1. And the displacement over which these astronauts will be catapulted is 1,800 kilometers. If we go with the regular runway, what's the acceleration? Right, so here's your side view here. Just like before, let's write down the quantities that were given and the quantity that we're looking for. We know what the displacement needs to be. We know the initial and the final velocities. We'd like to know what the acceleration is. So we'll go back to, I'm afraid that transition is going to happen again because I just copied and pasted the slide. Oh, okay. Yeah, it's getting old now, huh? We go back to this slide and ask ourselves, which of these equations would get us the answer we want most directly? And hopefully this one jumps out at you. One way this could jump out at you is to train yourself to be looking for situations where there's no mention of time. Remember, there's that one equation that's most useful if you don't need to deal with the time interval. No mention of the time interval in this problem, so we jump straight to what I call the v squared equation. I just call it the v squared equation. I can't think of a better name. So let's use this. And you'll notice previously, the notation I used was v initial and v final, but because of my choice of notation for the times here, I'm calling them time 0 and time 1. Let's also call the velocities v naught, that's the same as v0, and v1, right? Just a slight adaptation of the notation there. What are we solving for? Acceleration. Hopefully you can do that in your head. You're going to find that physics will make you better at algebra because you're doing a lot of simple algebra in this class. Now we plug in numbers. A word of caution, be careful with your units. I said that the final speed needs to be 8 kilometers per second. The safest thing is always to convert your numbers into SI units. As you get more sophisticated, sometimes you can take shortcuts, but for now, probably you just want to convert everything. So 8 kilometers is 8 times 1,000. So I've written 8 times 10 to the third meters per second now, and I'm squaring that whole thing. Notice I put the squared symbol outside the parentheses. The units are inside. So we're actually picking up units of meters squared over seconds squared. That's the dimension of the numerator, meters squared over seconds squared. How come I don't have the second term? Because it's 0. There was no need to write that, but we've got a minus 0 squared, you could say. Downstairs, I just plugged in that number 1800 because, oh, this is a typo. Did I write kilometers here earlier? I'm gonna have to fix that. Okay, in subsequent slides, it's probably going to say 1800 kilometers. That's way too long for a runway, right? So this should definitely say, oops, laser pointer. This should definitely say 1800 meters in the subsequent slides. All right, now you just evaluate. You just plug everything into your calculator. Let's check the units real quick. Upstairs, we have meters squared. Downstairs, we just have meters. So we're left with meters upstairs. And then 1 over second squared, we would put those seconds squared down in the denominator. So we do come out with units of meters per second per second. That's the SI unit of acceleration. If you plug SI units in, then SI units will come out. That's the safest thing to do. And one reason you need to use SI everywhere else is because if you plug in 9.8, it's understood that you're using meters per second per second. The free fall acceleration only has the value 9.8 if you're on Earth and you're using meters per second per second. If you were using imperial units, for instance, it would be 32 feet per second per second. If you were using light years per year, the number would come out 1, which is one of my favorite ways of expressing it, and I'll talk about that later. 18,000, can that be right? That's an extraordinarily large acceleration, right? I think it's fair to say you have never accelerated at that rate. How many G's is that? Let's compare that to the free fall acceleration. This is something we'll do often. Yes, G is a letter that represents the acceleration, but you can also think of it as a unit of acceleration. 1 G of acceleration is the same as 9.8 meters per second per second. So you can treat it like a different unit of acceleration, just like a feet per second, a meter per second. I said a moment ago, a light year per year, or just a G. So if we divide, I'm using the normal unit conversion, C meters per second squared cancels meters per second squared down here. You just have to divide by 9.8 and you get 1800 Gs. And let me point out a very simple result that you should keep in mind throughout the semester. If you're standing on a scale, gravity is what's pulling you into the scale, right? So the force of the scale on your body pushing back on you is 1 times your weight, right? Otherwise you'd be falling into the floor, right? So the scale pushes up on you with a force equal to your weight because of gravity. So if you're accelerating at 1800 Gs, maybe you can see how you have this makes sense to you, that the force on your body would have to be 1800 times your weight. So in summary, if you're accelerating at any multiple of G, then the force on your body is that same multiple of your weight. Does this sound survivable to you? Force on your body equal to 1800 times your weight. I mean, if you want a number, let's say you weigh 200 pounds, especially with your spacesuit on. 1800 times 200 pounds, 360,000 pounds. Let me divide that by 2,000 pounds, which is how many pounds are in a ton. That's 180 tons of force on your body. So which of those numbers is more meaningful? You could say it's 180 tons of force on you if you're 200 pounds, or you could just say it's 1,800 times your body weight. Either way, not survivable. It is not practical to launch astronauts into space using a system like this because nobody would survive. The only thing you could launch into space using a railgun that short would be indestructible type stuff, like just water. I don't think you can smash water just by accelerating like that. So water, oxygen maybe in some indestructible tank, Spam, Twinkies, cockroaches, stuff like that. Okay. So we can turn this problem inside out and say, well, what if we want the astronauts to be comfortable? First of all, we want them to survive, and we also would like them to be comfortable during this acceleration. So let's require that the acceleration is limited to 5 Gs, whatever 5 times 9.8 is. And I chose 5 because if you go to any theme park, even a place like Six Flags, I think that the greatest acceleration you're subjected to is something like 4 or 5 Gs. You see, 1 G is not exciting. That's not a thrill. But several Gs will put the thrill in thrill ride. The acceleration that your body experiences is what makes it exciting. But you don't want it to be too exciting. If you get up to 6, 7 Gs, half of the passengers on your ride are going to pass out. Some of them might even blow chunks, as they say. There's going to be people throwing up. That might be amusing to some people, but on the whole, not a satisfying thrill ride experience. Certainly not at Disneyland. That's not for the clientele at Disneyland. You can go on YouTube and watch pilots training for, like tight circles that you might do. Fighter pilots for sure would have to train this way. They subject them to high acceleration so that they can practice doing the things that they like. I think you can clench your leg muscles, various things you can do, change your breathing so that you don't pass out. But by the time you get up to 7, 8, 9 Gs, it's really hard not to pass out. So this is already at the upper end of what you would want to subject your astronauts to. So now we still know the initial and final velocities. That hasn't changed. It's the acceleration now that we do know, and what we're looking for is delta x. That's now the unknown variable. How long does this track need to be so that you not only don't kill your astronauts, but you don't make them faint before they get to space? So we start with the same equation because it's the same variables. This time we're solving for delta x. And there it is. Before I plug in numbers, I want to point out how flexible, not flexible, but how many situations you can apply this equation to. Just think about when you're driving. When you hit the brakes, let's say you were texting, you weren't paying attention, and you suddenly realize that the cars in front of you have stopped, you need to slam on your brakes, or maybe you see an obstacle in the road, debris, whatever. There's a limit to the rate at which your car can accelerate. And that really has to do with the amount of friction you can develop between your tires and the road. Like, you can't have any old acceleration you want. It's kind of like how if you slammed on the brakes and your wheels actually locked, it's not like your car is going to stop on a dime. It's going to skid and stop over some distance. Well, this equation right here tells you, let's assume that there's some fixed acceleration that depends on the friction between your tires and the road. This equation says that your stopping distance depends on the square of your speed. Your final speed in that instance would be 0 when you come to a stop, and V initial would be how fast you're going when you apply the brakes. So the stopping distance required depends on the square of the speed. And we're going to deal more with this later, but quadratic dependence like that means if you go twice as fast, 2 squared is 4, you would need 4 times the stopping distance. So when you're driving 60 miles an hour, you're going to need 4 times as much distance to stop as when you're driving 30 miles an hour. And that's why all those people, tailgating on the freeway are crazy. Oftentimes I see people less than 1 car's length from the back bumper of the car in front of them. And they just seem to be unaware that if something were to happen, there's not enough stopping distance, not even close. There's going to be a collision. Let me interject one more comment here. You know how when off in the distance, if you're in, let's say you're in class at the corner of Clark and Carson, and you hear a car accident almost happen, or maybe it did happen, you hear that squeal. Hopefully you don't hear the at the end of the, but the longer the sound, the longer that is, the better for the occupants of that vehicle, because it means they're stopping over a larger distance. Let me go back a couple slides to right here. Right? The longer that tire squeal is, the greater the distance over which they're stopping. That means the lower their acceleration. And that ultimately means the lower the force forces to which they're subjected from their seatbelt or the airbag perhaps. So it's very intuitive, but this equation that we've developed gives us a nice relation between those three quantities: speed, stopping distance or displacement, and acceleration. So get really comfortable with this equation. You can do a lot with it. Here's what I find. If I plug in the necessary final speed of 8 kilometers per second and my acceleration here, remember 5 G's was our upper limit, so 5 times 9.8, that would have to be a very long track. 650 kilometers is something like 400 miles. I mean, at that point, you can't even build it straight. You cannot build a level track at that distance because of the curvature of the Earth. So the Earth would actually be curving away from your track, and that means you'd have to have this enormous support structure. I suppose you could just have your launch vehicle move along that curved track, but that means you'd need additional forces to produce the curvature there. You can't just have the rocket out the back end. Something's got to make it deflect, and that means tremendous, you know, if you did that with some sort of some kind of brace attached to the track itself, then you've got additional stresses there. Yeah, we got Space Mountain over here off to the side. I believe this is a real photograph. You flat earthers out there, you know, if you're a flat earther, let me ask you something. Why are you not trying to buy real estate right at the edge? Wouldn't that be an incredible view? And I can't take credit for this idea. I heard somebody else say it, but it makes sense. If you really thought that the Earth was flat and there was an edge to it, you would want to have, you know, beachfront property. Or maybe not. That would be kind of horrifying, looking into the abyss like that. But notice how US is appropriately centered here. Okay, that's it for that. I will put up a video where I just work problems from chapter 2 and get some practice using these kinematic equations. But you're going to be seeing these many times over throughout the semester. When we get to chapter 4, we'll be doing kinematics in 2 dimensions along the X and Y axes simultaneously. Once you're comfortable with that, then we introduce forces. We look at pulley problems, things sliding down ramps, actual rocket problems, simple problems, and we will still be using kinematics, but we'll be using forces to predict the acceleration. So everything about this class is cumulative. The stuff you're learning now, you will be using at the end of the semester.